Hello everyone. Today we have with us Hrishik Koley for today's math club talk. He's interested in combinatorics and today he's going to talk about Tribone Tilings. Over to Hrishik.
Thank you, Devansh. So today we'll be talking about Tribone Tilings, Honeycombs to Benzels. But before delving deeper, we will try to decipher each and every one of these words to get to the results that we are going to do. So starting with the most basic one, tilings. I hope everyone has done at some point in their life this very simple question where we take a chessboard and then remove the two corner squares and try to tile it using dominoes. Dominoes are basically these shapes. So we have all proved at some point in our life that it is not tileable using 31 such dominoes. But as soon as you take an entire chessboard without removing its corner squares, you can tile it using 32 dominoes. You can check that for yourselves. So where does this idea of domino and diamond tilings come from? It arose in the intersection of physics and graph theory and has been considered from a while now. It originated back in the 1900s. So the classical domino tiling problem considers an m cross n rectangle and tries to tile it with dominoes, that is 1 cross 2 rectangles or 2 cross 1 rectangles. But any tiling problem at random considers a lattice structure and then considers a shape in that lattice, and you are given a set of tiles and you use only those set of tiles under translation and rotation and try to tile the shape given to you. If it is tileable without overlapping any of the tiles, then we call that an acceptable tiling. If it is not, then our tiling is not possible. So consider this 4 cross 4 rectangle. You can see a tiling given using the 1 cross 2 and 2 cross 1 tiles. So we will talk about how we reduce our domino tiling of a m cross n rectangle to a problem of perfect matching or diagonal cover in a graph. So I hope everyone knows the definition of a graph. It's basically a set of vertices and a set of edges defined where each edge connects any two given vertices. So, okay, if we take a set E dash, which is a subset of the edge set E, then a diagonal cover or a perfect matching of the graph is basically that set E dash with the property where each vertex belongs to at least exactly one of these edges. So consider this graph. Okay, before going to that, let's let me explain what a matching looks like. So just consider this graph with the following edges. So let's name these edges E1, 2, 3, 4, 5. So you will see that if you take the set of edges E1, E4 and E5, then these edges cover each and every one of these vertices exactly once. So this E1, E4 and E5 is precisely a perfect matching for this graph. Similarly, in the graph on the screen, you will see that the thicker lines, or if the color is visible from the back, the red lines constitute the perfect matching for this graph. Now, we take this entire graph along with its perfect matching and embed it in a tile. In a domino, and you will see that each and every perfectly matched edge corresponds to one tile in the 4 cross 4 rectangle. Remove all the edges that are not perfectly matched and you will get the exact orientation of the tiles to be used in the tile, and thus you finally reach at the domino tiling of the 4 cross 4 rectangle. Okay, so moving on, why do we consider tiling problems, or what are the main questions that we consider while talking about tiling problems? The first question that comes to our mind is a given shape in a particular lattice tileable using a given set of tiles? The second question that mainly arises is how many ways are there to tile a shape using a given set of tiles? There are other questions that are being considered, like whether some fault-free tilings are possible or not, but those are questions that are irrelevant to this talk, so we'll move. Okay, so coming to the second terminology, that is honeycombs. So what are honeycombs? Honeycombs are these roughly triangular structures in the hexagonal lattice. So you can see that each and every one of these boundaries of this shape has n many hexagons, and so we denote this honeycomb structure by T sub n. and the interior of this T sub n structure is occupied by a T sub n minus 3 honeycomb. So now, these are mainly the tiles that we use to tile the honeycombs and Benzels. These are called the tri-hex tiles, that is, it is a combination of 3 hexagonal tiles, and you can try to construct any other tri-hex tiling, but you will see that each and every one of them will be isomorphic to one of these 3. Okay, for the naming of these, we will stick to Propp and Thurston's convention. We will call this the stone, we will call this the phone, and this the bone or the tribones sometimes. So this is mainly the tile that we are interested with in this term. So coming to the theorem or the conjecture which Conway and Lagarias proved, and which has been given in the abstract, is that it is impossible to tile any honeycomb Tn using only tribone tiles. Okay, so before moving on into the proof and all, the best way to do any combinatorial problem is trying to reduce it into a simpler combinatorial problem. So our attempt would be to take this entire problem in the hexagonal lattice and convert it to a problem in the square lattice, as domino tilings or any polyomino tilings are the ones which are more generally considered. So let's try this. So consider this lattice, this is the R square lattice, and these intersection points belong to Z square, so these are called the lattice points. And these lattice points belong to Z square. Similarly, any two neighboring lattice points, and if they have a edge between them, then these two lattice points are called neighbors. And we call a cell the collection of the boundaries and the interior of 4 lattice points. So now we'll define what a directed path is. So let us start from any given lattice point, say here, and then we follow some random path. So any path that we can follow going from one lattice point, let's call this x0, y0, and let's just call it x and y. So any path from x0, y0 to x and yn in a particular direction or in an ordered way is called a directed path, and a directed path is called simple if in this entire path no edge appears twice or it does not cross itself. So what do we mean by crossing itself? So let's say we have this path P and it has 2 vertices xi, yn, or 2 lattice points xi, yn and xj, yj, which are equal for I not equals j. So then we say that it crosses itself. So yeah, if a directed path has no edge appearing twice and if it does not cross itself, then we call the directed path simple. So next we define what a region is. Well, a region can be thought of as the concatenation of many of these cells. Like you can take, let's take these cells. So yeah, so the combination of C1, C2 and C3, these 3 cells can be called a region. And now moving on, we'll talk about the boundary of these cells. So we take the boundary in a counterclockwise manner. So this path is the boundary of this cell C1, and the concatenation of all the boundaries of these cells C1, C2 and C3 gives the boundary for some region R. R is precisely this. And how do we get that? Well, consider the counterclockwise boundaries for each of these. So while we consider the counterclockwise boundaries for each of these cells, you will see that some of these edges have the boundaries in opposite directions, and thus we remove these edges from the set of edges belonging to the boundary of R, and this precisely becomes the boundary of R. Okay, moving on, people with some idea of topology would know what connected and simply connected means, but for a brief analogy on that, for any given region R, we call it simply connected if its complement, that is R square minus R, is connected. So what do we mean by connected? Well, if we can't represent this region as the disjoint union of two sets, then we call this connected, and thus R becomes simply connected. Considering an example for that. So consider this random tile, and consider it being embedded in the. So this is our tile. This is not part one. So consider this being embedded in a square lattice. So if you remove it, you can express it as the disjoint union of this entire area x and the entire outer area, which we will call 1. So as it can be represented in the as its complement is represented in the form x disjoint union y. So this type is not simply connected. Okay. So now moving with the idea of the boundaries, let's again consider a tile. So now for the boundary of any tile, we represented it using partial of R, and the point from which we start, or the lattice point from which we start considering this entire boundary, is called the base point, and we say that this boundary is pivoted at E1, and we represent it as partial of R. So the boundary of this pivoted at E1 would be simply this. But mind you that even if you don't consider E1, even if you start from some other lattice point E2, the boundary remains the same for any given time. And that's where another idea comes in. I'll go back to this in a moment. But yeah, that's where another idea comes in, is that if you are given some boundary of type R pivoted at E1, then it can be represented as the conjugate of any other type pivot, the conjugate of any other boundary of this type pivoted at any other lattice point. So what is W and W inverse? Well, instead of considering this as a directed path, we will represent it as a combination of words. So whenever we move in this direction, we represent it by an A or across. Whenever we go up, we represent it by a U or up. So, and the inverses are also used. So if we start at E1, we go about so if we start reading this entire word from right to left, then it precisely gives us the boundary for this tile pivoted at E. And now some changes to these can give the tiling in E3. Let's consider that. Yeah, Yeah, so this A square becomes our W and this A square inverse becomes our W inverse. So as you can see, the boundary remains the same in terms of the directed path, and this is precise. So we can say that the partial of the boundary pivoted at E2 is a conjugate So now, as you can see, that each and every one of these words is precisely a combination of U's and A's and A inverse and U inverse. So we can consider this to be a group generated by A and U. What is a group generated by A and U? Just a combination of A's, U's, and A inverse and U inverse. That's all. Okay. So another idea is of the tile type. So a tile type is precisely all the tiles that and their translations considered all together. And a tiling problem now, in a much more generalized sense, would be considering a lattice and then considering a region R in it. And let's say you are given a set of tiles sigma. So sigma consists of all, let's say, m number of tiles. So it has m many distinct tiles along with their translations. Okay, so what do we mean by translations here? Yeah. So let's say you are considering a tiling using this L structures. So in one of these tilings you can use two of these L structures placed side by side, and the others will fit up some other structures that we need not think of right now. So yeah. So this can be the position of the L tiles in one of the tilings and some other tiling some other tiling may just place the L tile here. So in this tiling of this shape, let's say that we just are considering these part of the square, that is, this is our region. So in some other tiling, these L tile can occur in this position, but if we try to place the L tile here in the same position, then it overlaps with these two L tiles, and this is not possible. So the translation of a tile is basically that each and every position that it can be placed in. That's all. Yeah. So thus the generalized tiling problem boils down to considering a lattice and a region in the lattice, and given a set sigma of tile types, we consider the question whether the region R can be tiled using the set of tile type sigma. Now, these boundary that we talked about here is the topological boundary for each and every one of these regions. But the idea of topological boundaries can be generalized to consider the idea of combinatorial boundaries, which we denote by this, which is the set of all the possible boundaries pivoted at any EI belonging to the vertices of the tile. So it precisely is all the words that you can use to represent the topological boundary of this type. So we have this thing called the tiled group. But before that, we will represent something called a cycle group. So we represent cycle group by C. It is precisely a subgroup of this group F. So C is a subgroup of this group F, and it corresponds to all the closed directed paths in the square lattice. So anyone who knows a bit of graph theory, you can just think of it as any cycle, any directed cycle in the square lattice. And now what the tile group is, well, it also is a subgroup of F, but more importantly, it is a subgroup of C2. Yeah, so the tile group is basically the group generated by So it's basically the group generated by all of the possible tiles pivoted at any point and all of their conjugacies placed together. So next is a simple definition of a tile homotopy group. We will not be using that idea, but just to not miss out on it, I have included it here. So anyone who is familiar with homotopy will know that this is an analogous to the first homotopy group. It is simply given by C quotient, the cycle group quotient the time. So this 8 sigma represents the tile homotopy group. We will not be using that idea, so it wouldn't be necessary for the proof. Now, before we go into the proof that no tribone tilings are possible for our given structure of the honeycomb, we need to define some constraints or some conditions under which tiling of these honeycomb structure is possible using trilix tiles. For that, one of the simpler conditions is, okay, let's try to take an intuitive idea of this. So if you are given some combinatorial boundary, partial of R, and you are given some tile with T sigma, then you can see that T sigma is basically the boundaries of all the tiles that are being considered put together. So if you can take some tiles from T sigma and the combination of their combinatorial boundaries, or the concatenation of their combinatorial boundaries forms the combinatorial boundary for this region R, then we say that this region R is precisely tileable by the tiles present in sigma. The proof is not that easy, but I'll not be going into the proof, as that will extend this talk way too much. So if you want, you can check out the proof from the references that I will add. So yeah, so the theorem goes as follows, that a simply connected region R has a tiling by tiles in a set sigma only if the combinatorial boundary partial of R be contained in the tile group T sigma. Okay. So another condition would be, as all of you have seen the structure honeycomb tilings. As I've told that its outer boundaries have its three outer boundaries have n many hexagons, and its interior has t n minus 3 many. So you can check the picture and you will find that this Tn has precisely n into n plus 1 by 2 hexagonal cells that are to be covered using the tiles. So it is pretty obvious from there that if and only if n is 0 or 2 mod 3, only then is this total number of hexagonal cells n into n plus 1 by 2 divisible by 3, and thus that is the only case where it is trivial. You can find a simple contradiction for the case where n is 1 mod 3. So now we will be reducing the entire problem that we have at our hand to the square lattice, and this critically simplifies our problem. So we have the honeycomb lattice, and we will be reducing it to what we will call the stairs. So consider this. Yeah, I'm not very good at drawing. So this is the T4 honeycomb, and this reduces in the square lattice to this lattice. So we represent this by T-4. So this structure in the hexagonal lattice reduces to this staircase structure in the square lattice. And now, as we were talking about the boundary some time ago, so the boundary of this T-4 structure will precisely look like this: an u n inverse u n. So now, as we have converted the shape to be tiled to the square lattice, we surely need to convert the tiles that we use for the tiling to the square lattice, because well, it's not possible to tile this using some trilix tiles. So this was our tribone tile. This reduces to one of these 3 tiles in the square lattice. Now you will try to construct any other tile using 3 squares, and it either is isomorphic to one of these 3, and for all the other structure it corresponds to either the stone tiles or the foam tiles. The only other possible cases could be something like this, and or the rotations of this, or something like this. So this corresponds to the stone tiles, and this corresponds to the foam tiles in the square lattice. So you can again check the combinatorial boundaries for each of these. That will be pretty easy. Next, we move on to what we call the Koley diagram. So we consider a group. We consider a quotient group G, which is Fg quotienter K, where Fg is a free group generated by some G many generators. And K is a collection of relations on this. So what the analogy for K will be, I will come to that in a moment. So for any of the Koley diagrams, you take each and every vertex present in G, you assign each and every element present in G of vertex, and let's say you have this vertex W. So for W belongs to G, and let's say you have G many generators S1 through SG. Then you introduce a directed edge from W to SIW and give this directed edge a weight I. And similarly, for each of these, for some Sj, you give this directed edge a weight J. So you will notice that each and every one of these vertices in the Kelly diagram has a degree 2G. That is G many edges going outwards corresponding to each of these generators, and there will be G many edges coming inwards. From SI inverse W and some SG inverse W. So W will have, or any vertex corresponding to some element in G will precisely have 2G edges incident at G many going outwards and G many coming inwards. So okay, for understanding this K, which is the normal subgroup of relations for us, it is if we start at consider any given graph, so the picture is here. So this is what we call the identity vertex. So now if we start from this identity vertex and move around this Kelly diagram corresponding to some word, then if we return to this identity vertex, then that particular word, let's call it W, belongs to K, and thus K is just a collection of all such W's. So so now we will be defining a special subgroup whose idea we will be using for the proof. We call this special subgroup H, which is just the quotient group F2 by H. F2 is precisely the free group generated by this A and B. And we also define a corresponding undirected Kelly diagram. That is, here you will see all the directed edges. You just remove all these directions, and we define it as G complement F2H. So now the subgroup of relations for us, which earlier for the general case was K, in this very particular case, or for a special subgroup, it will be the normal subgroup generated by you can check for each and every one of these cases. It returns to the identity vertex. So you start at I, you go about 3 U's, you take the path along U, return to it, you take the path along A, you return to it, and then A, U inverse, A, U inverse, A, U inverse, you again return. So, okay. So now we'll consider another theorem, which is that the tile group T sigma and the combinatorial boundary for any given region partial of Tn for n being 0 or 2 mod 3, all of these are contained in H. This will be pretty obvious to see, from the idea of the quotient group and the Kelly diagram. I'll not be going into the proof. You can again check out the proof from some of the references that I'll add later. Okay, so now for the proof we define a homomorphism, but before going into the homomorphism we define the idea of what we call the winding number. So we represent this winding number by W, and it takes parameters T and S, where T is a path and S will be a stem. So the winding number for any closed directed path P in this so any winding number for any closed directed path in the G complement F to quotient H would count the number of times this path P goes around G complement and it encloses any given cell S. So the expression for that comes out to be, okay, it's given on the board, I'm not writing it also. Yeah. So the expression for this winding number for any given path and any given cell comes out to be 1 by 2 pi I, and the surface integral over P 1 by z minus xs dz. So xs is just any point present in the interior of the chosen cell S. So now you can also check by doing some computations on these expressions that the concatenation of any two paths P2 and P1 would be just additive in nature. That is, when it's given here that the winding number for any concatenated path P2, P1 with the cell S is basically equal to the winding number of P2 enclosing S and P1 enclosing S. So, okay. Now, if you are given a collection of set S, capital S, so for that, the winding number for that finite or infinite set of cells will be precisely the winding number for the path enclosing each and every particular cell S, small s, in the given set capital S. Okay, so now that we have defined what this winding number is, so we define a homomorphism phi from each to the set of integers z, and we define it as phi v given S, where the set of cells S is basically the set of all the hexagons present in the KD diagram. And now the final step for our conjecture would be, from the definition, as I said, we name each of these tiles so for each of these tiles, the value that this homomorphism phi gives is 0 for any of these combinatorial boundaries. We'll check for one of these tiles and the rest can be done in a very similar method. So let's go back. And also write down the expression for that. So so the combinatorial boundary for this R3 tile was A U inverse cube and A inverse U cube. So now let's start at this identity vertex of the KD diagram. So we move along and A U inverse A U inverse A U inverse, we return to identity. We have done 3 iterations of that, and then we again do 3 iterations of A inverse U, A inverse U, A inverse U. So this entire combinatorial boundary encloses, it encloses this upper hexagon in a clockwise manner and this lower hexagon in a counterclockwise manner, and thus it cancels out both, thus giving us that phi is precisely 0, as it winds around this hexagonal cell S one time and this hexagonal cell S minus one time. So just see. So in the same way, you can check for the values given by the combinatorial boundaries of R1 and R2. Now, as we have seen that for any given tile Ri, no matter which vertex we pivot it on, we can convert it to another combinatorial boundary for the same tile pivoted at a different vertex by a conjugate of it. So it is pretty easy to see that the values generated by the function phi for any of the conjugates will always be equal. So going forth with that idea, you can again use the Koley diagram to check that for any of these staircase graphs T dash n, the number given as output by this phi function will be n plus 1 by 3. And so we can represent the entire combinatorial boundary for this T. Okay, so now let us prove by contradiction that this entire combinatorial boundary of this staircase region that we have this staircase region that we had, this let us assume that this belongs to the tile group P sigma, where sigma is just R1, R2, R3, and all of their translations. So the combinatorial boundary can now be expressed as a product from I equals 1 through m and some conjugate of the combinatorial boundary of some given tile pivoted at some point. So now using the additive property, you can see that the additive property of the winding number, you can see that the value given out by phi for the combinatorial boundary of the staircase graph will be 0, which is a contradiction to the fact that we got n plus 1 by 3. And so this, the combinatorial boundary P n dash is not contained in the tile group P sigma. And thus Conway and Lagarias came to the conclusion that the Tn is not tileable using tribones. Now moving on to Benzels tilings. Well, this entire proof that a honeycomb structure is not tileable using some tribone tiles was given by Conway and Lagarias back in 1988. So that rendered these tribone tiles pretty much useless for some decades. But then just back in 2021, James Propp came up with the two-parameter family for a structure in the same hexagonal lattice, which he calls the Benzels. And then this two-parameter family takes two parameters A and B constrained to the fact that A is less than equals to B minus 2 and B is less than equals to A minus 2. So here you can see a picture of the 5-7 Benzel. Well, so why the name Benzel? The first idea that he has was from the chemical element benzene, whose hexagonal structure is reminiscent in this Benzel. The second was from the car company Mercedes-Benz, and the third was from the merry-go-round inventor Gustav Benzel. As just like in a merry-go-round, this Benzel structure has a threefold rotational symmetry. And how does Mercedes-Benz become an inspiration for this? That will be obvious when we construct the Benzel. So let us consider the 4-6 Benzel. So for any of these Benzel, you start at a point and the structure is drawn using, just as you can see, that 4 lines and 6, then 4, 6, 4, 6. So just this part was reminiscent to him of the symbol of the car company Mercedes-Benz. So That's why he got an inspiration from there. So you can draw this, and then you precisely get the boundary for this Benzel structure, and then all that's left is just placing the hexagons, and you achieve the Benzel structure. So yeah, so it pretty much uses the same tiles that had been introduced for the honeycomb tilings, but as this is a very new field, so the phone tilings are not being considered as of now. We mostly consider the tribone tilings and the stone tilings. So for our purpose, we will just be considering the tribone tiling. So let's consider this 5-7 Benzel. You can see two different tribone tilings given for this 5-7 Benzel, but what's interesting to see is that this 5-7, after this 5-7 Benzel, the next Benzel that admits only tribone tiling is the 12-15 Benzel. This follows an interesting pattern that Propp and Kim came up with, that the AB Benzel can be tiled by tribones if and only if A and B are paired pentagonal numbers. That is, here you have the form k3k plus 1 by 2 and k3k minus 1 by 2 for some possibility of 2. Well, now, back in 1988, when Conway and Lagarias wrote the paper for the proof that honeycombs are not tileable using tribones, there was this follow-up paper by Thurston who introduced a very interesting idea of shadowing paths and winding and wheeling. So it uses the Gauss-Shoelace formula and extends it to a different kind of unit vectors, or a different set of unit vectors to say. So the Gauss-Shoelace formula precisely goes like this. I believe everyone is familiar with this. Yeah. So now, normally, for us, the unit vectors have always been I, j, minus I and minus j. But we scrap that idea here. We will, going forward, we will be using these set of unit vectors to as the vectors for the hexagonal field. Where we have A minus A, C minus C and B minus B. And when they are put together in a hexagon, they follow exactly this pattern. Yeah, as you can see on the screen. Okay, so now we define some C. Which is the modulo value of A plus B mod 3. So now C can take precisely 3 values, 0, plus 1 and minus 1. So consider this. We'll not be considering this because we'll just be proving for this and everything else follows in a similar manner. So this is the class 0 Benzel, and the upper stretch or the upper boundary of this class 0 Benzel would look like this, and the lower boundary would look like this. You can check that through any Benzel structure. So now, we consider for C equals 0. And as we already defined in the combinatorial boundary that we always follow a counterclockwise direction. So for the upper stretch, we start from the upper right corner, that is this one, and move on to the upper left corner. So this will just be a concatenation of So this will just be a concatenation of so from this point onwards, just to write less, I'll be representing minus a by a dash, minus b by b dash, and minus c by c dash. So yeah, so the upper stretch will be a concatenation of t many of these, where t is precisely 2b minus a by 2. And for the lower stretch, we will, following the same counterclockwise logic, we will start from the lower left corner and go towards the lower right corner, which gives us this s many times to form the lower stretch where s is equals to a minus b by 3. So now the counterclockwise boundary of the Benzel starting at the rightmost corner of the bounding hexagon will simply be a concatenation of these 6 sets of unit vectors, repeated s or t many times as and when necessary. And you can check that this involves precisely 12s plus 12t unit vectors. Now, a revision of the Gauss-Shoelace formula for this hexagonal grid gives us that the formula will now change to something like this, where we take any two of the unit vectors in 12s plus 12t, and then we have the cross product for that. So there is a very computation heavy way to compute this, but if we consider this in a more combinatorial way, the computation can be made a bit easier. So you can always check that there are 12s plus 12p choose too many product terms which can be segregated into 336 terms. How do we come up with this 336? Well, as you had seen in the pair of 4 unit vectors, these positions had the unit vector x dash. So for some cases this x dash will be same. So whenever these x dash is same, we choose 6c1, and when we are taking x dash for the rest of the 2 positions, we do not consider x, rather we fill this up independently with some y and z, for each of which it comes out to be 4c1 plus 4c1. And in some cases we will have distinct x dash and y dash in these places, so we get to choose 6c2, and for the rest of the places we again choose 4c1 plus 4c1, which gives us precisely 336. Into 336 times into which this terms vi plus vj can be segregated. Now this entire thing becomes a quadratic function of s and t, and as we had seen that s and t can be represented in terms of a and b, so this ultimately boils down to a quadratic function of a and b. Now consider some 6 Benzels of this class 0 type, and if you take the system of linear equations for each and every one of these, you will finally come to an easier computation that will help you get the 6 undetermined coefficient. Doing this entire computation, you can check that the area of this class 0 Benzel comes to be equal to minus a square plus 4ab minus b square minus c minus b by 2. And similar process follows for the class minus 1 and class plus 1 Benzels, which gives us these formulas or these values for the area of any region R, where R is a Benzel of class C. So now there was another concept that was defined by Thurston in his paper back in the 1990s called shadowing of paths, which he used to compute something called the rescale Conway Lagarias Conway Thurston invariant, and he denoted it by small r and r. So, okay, we say that at any point I, a path weaves if the edges ei minus 1 and ei plus 1 are parallel to each other, and at any point I, a path winds if none of the edges ei minus 1, ei and ei plus 1 are parallel to each other. Now, if we are given some path, say pi, we can determine a shadow path or define a shadow path pi dash by making the path weave wherever it winds and wind wherever it weaves. So using that same idea of constructing the shadow paths, we can define the shadow paths for a right stone and a left stone, giving their Conway and Lagarias invariant to be +3 and -3. But as we are not concerned with them, I will not compute this. Rather, I will go on to compute the Conway and Lagarias invariant for the Tribone Tilings. So now we start with 1, 2, 2, and as in this path 1, 2 and 3 is winds, so we weave here, this weaves, so we wind here, 3, 4, 5 weaves, so we again wind here, 4, 5, 6 weaves, so we wind, 5, 6, 7 weaves, we wind again, 6, 7, 8, this winds, so we weave in this position. And then again 7, 8, 9 winds, so 7, 8, 9, yeah, 7, 8, 9 winds, so we weave, 8, 9, 10 winds, so we weave again. And following this pattern, we reach this dumbbell structure. So this dumbbell structure follows this path. So now, as we had done, the combinatorial boundary is always considered in the counterclockwise direction. So this one, or this hexagon, has the counterclockwise direction boundary. So we consider its sine area to be +1, and the sine area of this would be -1, as its combinatorial boundary is in the clockwise direction. And thus we get that the Conway and Lagarias invariant for this tribone would come out to be 0. Now, using the same idea of weaving and winding, we can compute for any Benzel R of class C that the unrestricted Conway and Lagarias invariant of R comes out to be these terms for the corresponding C equals 0, C equals +1 and C equals -1. This is very easy to check, you can check it out for yourselves. Now, the answer to a conjecture, considering just the C equals 0 case, because this is fairly computational in nature to check that for the class +1 Benzel and class -1 Benzel, there is no way that the Conway Lagarias invariant of this Benzel can be 0. And for the class 0 Benzel, it comes out to be 0. It comes out, the Conway Lagarias invariant for this entire Benzel R comes out to be 0 if and only if A and B are of the form for some positive integer k, thus precisely coming to the conjecture that James Propp and Jessica Kim gave. And so the main motivation for going through this entire process was that Conway and Lagarias failed to make any meaningful use of the tribone tiles, whereas James Propp came in introducing a new two-parameter family on the hexagonal lattice, where these tribone tiles can finally be put to use. Now, being a very recent field of development, these Benzels tilings are still being considered. If anyone gets interested in these Benzels tilings, you can check out James Propp website titled Benzels Tilings. So moving on, these are some of the references. If you want to know just about tilings, you can refer to the paper on tilings by Artin and Stanley. If you want to get the details of the proof for these tribone tilings for Benzels, you can refer to the paper of pentagonal number theorem for tribone tilings by Propp and Kim. And if you want to look at the results of tribone tilings on the honeycombs or other stone tilings on honeycombs, you can look at the paper Tilings with Polyominoes and Commentary and Group Theory by Conway and Lagarias. And this very interesting idea of winding and weaving and shadow paths was given by Thurston. So here we used it in a very intuitive manner, but there's a lot of mathematical detail that goes into this, which was not possible for me to cover. So if you're interested in that, you can look at the paper Conway Styling Groups by Thurston.
Does anyone have any questions? So let's thank the speaker again.